Your teacher today is Dr. Bbosa Science. Dr. Bbosa is a teacher at the Science Foundation College, the best school that teaches sciences. Today we are going to study A-level modern physics, lesson 3, an experiment to show the variation of current I with the PDV of a photocell. The setup is shown below. A monochromatic light or light with constant frequency is used. The photocurrent I is measured for increasing values of V at constant light intensity. For negative values of V, the polarity of the battery is reversed. The experiment is repeated by increasing the intensity of radiation by moving the light source closer to the photocell. A plot of the graph of photocurrent I against the PDV is shown below. Note that the current increases with intensity due to increase in the number of photons striking the cathode, and thus the number of photoelectrons. B, for each light intensity value, there is a maximum current that can be obtained called the saturation current. It occurs when the anode collects all the photoelectrons emitted by the cathode. C, the photocurrent is not zero when the PD is zero, because electrons are emitted with varying velocities or kinetic energy. Hence, some of the electrons have sufficient energy to overcome the repulsive electric field and make it to the anode. Example 1. A photocell is connected in the circuit as shown in figure 1 above. The cathode is illuminated with monochromatic light of wavelength 390 nanometers, and the current I in the circuit is recorded for different PDV applied between the anode and the cathode. The graph, figure 2, shows the results obtained. A. Find the maximum kinetic energy of photoelectrons. Solution. From the graph, Vs is equal to negative 1.0 V. Kinetic energy maximum is equal to 1.0 EV is equal to 1.0 times 1.6 times 10 to the power negative 19. This is equal to 1.6 times 10 to the power negative 19 joules. B. What is the work function of the cathode in EV? From Ke maximum is equal to Hc over lambda minus W naught. W naught is equal to Hc over E lambda minus Ke maximum. This is equal to 6.64 times 10 to the power negative 34 times 3.0 times 10 to the power 8 over 1.6 times 10 to the power negative 19 times 390 times 10 to the power negative 9 minus 1. This is equal to 2.19 EV. C. If the experiment is repeated using monochromatic light of wavelength 310 nanometers, where would the new graph cut the v-axis? From Ke is equal to Hc over E lambda minus W naught, 6.64 times 10 to the power negative 34 times 3.0 times 10 to the power 8 over 1.6 times 10 to the power negative 19 times 310 times 10 to the power negative 9 minus 2.19 is equal to 1.83 EV. Hence, the graph would cut the v-axis at negative 1.83 V. Example 2. 100 milliwatt beam of light of wavelength 4.0 times 10 to the power negative 7 meter falls on a cesium surface of a photocell. 1. How many photons strike the cesium surface per second? Solution. E is equal to Hc over lambda. This is equal to 6.64 times 10 to the power negative 34 times 3.0 times 10 to the power 8 over 4.0 times 10 to the power negative 7, which is equal to 4.98 times 10 to the power negative 19 joules. The number of photons per second n is equal to total energy over energy of one photon. This is equal to 100 times 10 to the power negative 3 over 4.98 times 10 to the power negative 19. This is equal to 2 times 10 to the power 17 photons per second. 2. If 80% of the photons emit photoelectrons, find the resulting photocurrent. Solution. The number of electrons emitted is equal to 2 times 10 to the power 17 times 80 over 100, which is equal to 1.61 times 10 to power 17. Current is equal to NE is equal to 1.61 times 10 to power 17 times 1.6 times 10 to power negative 19, which is equal to 2.57 times 10 to the power negative 2 amperes. Calculate the kinetic energy of each photoelectron if the work function of cesium is 2.15 eV. Kinetic energy is equal to Hc over E lambda minus W naught, where Hc over E lambda is energy in eV. This is equal to 6.64 times 10 to the power negative 34 times 3 times 10 to the power 8 over 1.6 times 10 to the power negative 19 times 4.0 times 10 to the power negative 7 minus 2.15. This is equal to 0.96 eV. This is equal to 0.96 times 1.6 times 10 to the power negative 19 equal to 1.54 times 10 to the power negative 19 joules. Or kinetic energy is equal to Hc over lambda minus W naught. This is equal to 6.64 times 10 to the power negative 34 times 3 times 10 to the power 8 over 4.0 times 10 to the power negative 7 minus 2.15 times 1.6 times 10 to the power negative 19. This is equal to 1.54 times 10 to the power negative 19 joules. Differences between X-ray production and photoelectric effect. In photoelectric effect, magnetic radiations fall on the metal surface and emit electrons. In X-rays, fast moving electrons hit the metal target, and X-rays, electromagnetic radiations are produced. In photoelectric effect, little heat is generated. In X-rays, a lot of heat is generated. Experimental evidence for quantum theory. 1. Photoelectric effect. To liberate an electron from a metal surface, a quantum or a packet of energy called work function is required, i.e. HF minus W naught is equal to a half mv squared, where W naught is the work function. 2. Optical spectrum. A line in optical emission spectrum indicates the presence of a particular frequency f of light and is considered to rise from a loss of energy which occurs in an excited atom when an electron jumps directly or in steps from a higher energy level E2 to a lower energy level E1. The frequency of the packet of energy emitted is given by HF is equal to E2 minus E1. 3. X-ray line spectrum. Electron transition from one shell to another leads to liberation of energy in packets, characteristic of the target atom. Differences between classical theory and quantum theory. The classical theory allows continuous absorption and accumulation of energy. In quantum theory, no continuous absorption is allowed. The energy is either absorbed or rejected. In classical theory, the energy of a radiation is evenly distributed over the wave front. In the quantum theory, energy is radiated, propagated, and absorbed in packets called quanta or photons. In classical theory, what matters is total energy of the incident radiation or beam. In quantum theory, what matters is energy of individual photon.